Welcome to our deep dive into the world of nanocatalysis. We've got a fascinating lecture here all about it. And while it might sound a bit technical at first glance, it actually affects a whole lot of things we encounter every single day.
Absolutely. And it's amazing how something like nano, it sounds so futuristic, but nature's actually been using this concept for millennia.
So we're really talking about like tiny particles that do big jobs.
Exactly. Think about enzymes for a second. Those are basically natural nanocatalysts, hard at work in all kinds of things, like helping us digest our food
Yeah.
or, creating things like bread, beer, and wine.
Oh, wow. So those microscopic processes are actually examples of nanocatalysis. Huh. I guess I'll never look at a loaf of bread the same way again. And the lecture also mentions our cars use nanocatalysis, right?
Absolutely. The catalytic converter in your car uses precious metals that act as nanocatalysts to help clean up those exhaust emissions.
So even though nanocatalysis might sound complex, it's already all around us. But this lecture goes even deeper, doesn't it? Like into some cutting-edge research.
Yeah, it really does. It explores how we can design even better nanocatalysts to solve some of the biggest challenges facing humanity.
Challenges like what specifically?
Well, the lecture lays out a pretty clear goal. Figuring out how to best design and use these tiny particles to tackle big issues in energy, medicine, and the environment. It starts by taking us through the history of catalysis, highlighting some of the biggest milestones that really changed the course of history.
Milestones like what, for example?
Things like the development of ammonia synthesis, for fertilizer, oil refining for energy, and of course we can't forget those catalytic converters we just talked about. These breakthroughs, they led to things like huge population growth and industrialization.
Yeah, it's crazy to think how those discoveries really shaped the world we live in today.
And one particularly striking example from the lecture is the Haber-Bosch process for ammonia synthesis. The lecture actually claims that without this process, only half the global population could exist today.
Wow, that's a pretty dramatic statement. Really puts things into perspective.
For sure. And it really just underscores the importance of catalysis. Now looking to the future, the lecture points out that we are heading towards a world with 10 billion people by the end of the century.
10 billion. So how are we going to support that many people while also protecting the planet? That seems like an enormous hurdle.
Exactly, and that's the exact question that this lecture grapples with, and it points to nanocatalysis as being a key part of the solution.
So these tiny particles are going to help us solve huge global problems. That's amazing. What are some of the ways it can actually do that?
The lecture highlights a lot of interesting areas, things like biomass utilization, turning CO2 into useful products, and developing cleaner and more efficient sources of energy. These are all areas where nanocatalysis can play a crucial role.
It's just incredible to think that something so small could have such a massive impact. And the lecture also mentioned that something like, what was it, 80 to 85% of synthetic materials rely on catalysts in some way.
Yeah, it's true. The scale of the chemical industry is mind-boggling. Just think about companies like BASF, Sinopec, Dow. These are huge companies. And even small improvements in things like catalytic efficiency can have a massive ripple effect throughout the world.
It sounds like there's a lot at stake,
Mm-hmm.
but I'm still a little fuzzy on how it all actually works.
Yeah.
Can we maybe go back to the catalytic converter example for a minute?
Of course. So remember that honeycomb structure we mentioned? Well, that structure is coated with a special wash coat, and that's where the magic happens. It's designed to help spread out those precious metal catalysts like platinum, palladium, and rhodium and maximize their surface area.
Got it. So it's like creating a bigger playing field for those tiny particles to do their work.
Exactly. And that's how they can actually effectively transform harmful exhaust gases into less harmful ones. It's a pretty brilliant example of how we can use catalysis to address real-world problems.
It really is amazing how something so small can do so much. But before we move on, there's something I've been wondering. Is nanocatalysis actually something new, or is it just a fancy name for something we've always been doing?
That's a great question, and it's actually a bit of a point of debate. Some people argue that all catalysis, by definition, happens at the nanoscale. But the lecture makes a really compelling case for nanocatalysis as being its own distinct field.
So what makes it distinct then?
It's the intentional design and manipulation of materials at the nanoscale to achieve performance that traditional catalysis just couldn't. We're not just observing what happens at the nanoscale, we're actively controlling it.
So it's like moving from just observing nature to actually becoming architects of this nano world.
Yeah, exactly. And that level of control gives us a whole new level of precision and possibilities. The lecture uses the analogy of gold. Like, in its bulk form, it's pretty inert, but at the nanoscale, gold can become incredibly reactive and very useful as a catalyst.
So it's about unlocking the potential of materials by shrinking them down to this nanoscale. That's a pretty powerful concept. Are there any other examples like that?
Oh, absolutely. The lecture mentions cobalt oxide. In its bulk form, it needs these high temperatures to oxidize carbon monoxide, but as nanoparticles, it can do the same job at much lower temperatures, saving a lot of energy in the process.
So not only can we make things work, we can make them work better, more efficiently, and with less environmental impact. That's the real promise of nanocatalysis, isn't it?
It is, and it all ties into this bigger picture of sustainability. Nanocatalysis isn't just about tweaking reactions, it's about tackling these huge challenges like climate change and resource scarcity.
The lecture specifically mentions CO2 to fuel conversion and water to hydrogen conversion as major areas of research. It's exciting to think that these tiny particles could be the key to a more sustainable future.
It really is a fascinating frontier of science. But before we get too far ahead of ourselves, let's take a step back and really explore some of the fundamental principles behind nanocatalysis. Because to understand where we're going, we need to understand how it all works at the most basic level. So one of the cool concepts to really grasp here is that nanocatalysis, like all catalysis, is about manipulating kinetics, not thermodynamics.
Okay, I vaguely remember those terms from chemistry class, but could you maybe remind me what the distinction is again?
Of course. So thermodynamics tells us whether a reaction is even energetically favorable. Will it happen spontaneously or not? But kinetics is all about the speed of a reaction. A reaction might be thermodynamically favorable, but it could happen incredibly slowly, like rust forming on metal.
Ah, okay, I see. So it's kind of like knowing which way a ball will roll down a hill versus how fast it will actually roll.
That's a great analogy. And catalysts, no matter what size they are, they don't change the direction the ball rolls, they just change how fast it gets there. And they do this by lowering what's called the activation energy, which is like, the initial push that ball needs to actually start rolling.
Gotcha. So catalysts don't change the outcome, just the speed at which it happens. But how does a tiny particle actually do that?
Well, the lecture describes this fascinating cycle. You've got your reacting molecules, let's call them A and B, okay? And they bind to very specific sites on the catalyst's surface. This close proximity, it facilitates the reaction between A and D to form a new product, we'll call it C, and then C detaches from the catalyst, leaving it free to start the cycle all over again with new A and B molecules.
So the catalyst is basically acting like what? A matchmaking platform, bringing the reactants together in just the right way.
Precisely. And what's really remarkable is that the catalyst itself isn't actually consumed in the reaction. It participates, helps things along, and then it gets regenerated, ready to do it all over again, millions, billions of times.
That's incredible. And the lecture mentions there are different types of catalysis, right? Something
Yeah.
about homogeneous and heterogeneous.
Yeah, that's an important distinction. So in homogeneous catalysis, the catalyst and the reactants are all mixed together in the same phase, usually in a liquid solution. Think of it like adding sugar to water. Everything just kind of dissolves and mixes uniformly.
So everything is one big, happy reactive family.
Exactly. But in heterogeneous catalysis, the catalyst is actually in a different phase than the reactants. Often you have a solid catalyst interacting with gases or liquids, like the catalytic converter we talked about earlier, solid metal catalysts interacting with those exhaust gases.
Okay, so more like oil and water. They don't mix, but they can still interact at the interface. So what are the pros and cons of each approach?
Good question. Homogeneous catalysts offer really good control over the reaction, but separating them from the products afterwards can be kind of a challenge. Heterogeneous catalysts are generally more robust, easier to recover and reuse, but sometimes they can be a little less selective, meaning they might produce some unwanted byproducts.
Ah, okay. So each type has its own strengths and weaknesses. So where does nanocatalysis fit into all of this then?
Well, that's where things get especially interesting. Nanocatalysts, they can actually bridge the gap between those two approaches. They can have the high activity and selectivity of homogeneous catalysts, but also keep the durability and reusability of heterogeneous catalysts.
So kind of like the best of both worlds. But if nanoparticles are so incredibly tiny, how do they even stay stable? I mean, wouldn't they just clump together or get lost in the mix?
Yeah, that's a critical challenge, and researchers are actively trying to address it. The lecture highlights strategies like using protective coatings, to prevent that clumping or embedding those nanoparticles within these porous materials to kind of keep them dispersed and accessible to the reactants.
So it's not just about the nanoparticle itself, it's about the environment you create for them to do their work.
Exactly. And this is where the nanoscale gets really, really fascinating. The actual size and shape of a nanoparticle, as well as the support material it's attached to, can dramatically influence its properties as a catalyst.
It's like tailoring a tiny machine for a very specific job. But do researchers really have that level of control over it?
They're getting there. The lecture describes how researchers are using all these really advanced techniques, from things like high-resolution microscopy to very complex computer modeling, to really understand how a nanomaterial structure dictates its behavior.
It's like unlocking these design secrets of the nano world. And as we learn more, are we finding that nanocatalysis can actually do things that traditional catalysis just couldn't do?
Absolutely. The lecturer points to several examples where nanocatalysis is leading to these entirely new possibilities. Like it's playing a crucial role in things like renewable energy technologies, things like fuel cells and solar energy conversion. And it's being used to create new materials with amazing properties like self-healing coatings and these incredibly strong, lightweight composites.
It's mind-blowing to think that these tiny particles could be the key to a more sustainable and technologically advanced future. But I'm guessing it's not all smooth sailing, is it?
Yeah.
What are some of maybe the challenges that researchers are facing when it comes to working in this field?
You're absolutely right. It's not all easy breakthroughs. The lecture actually spends quite a bit of time talking about the challenges of nanocatalysis.
Yeah, what are some of those, like, what are the biggest hurdles that researchers are trying to get over?
Well, working at the nanoscale, it comes with its own unique set of difficulties. One of the biggest ones that the lecture highlights is controlling the size and shape of these tiny, tiny particles. Even the slightest variations at that level can totally change how they behave as catalysts.
It's like, I don't know, trying to build a skyscraper with Lego bricks the size of atoms. You need just incredible precision to get it right.
Yeah.
So how do researchers even begin to approach that level of control?
It's a fascinating blend of chemistry, physics, and engineering, really. The lecture talks about a bunch of different synthesis approaches, everything from like very carefully controlling chemical reactions to using physical deposition techniques to basically grow nanoparticles with the exact characteristics they're looking for.
Wow, it sounds so complex. And I mean, once you've created these nanoparticles, how do you make sure that they actually stay stable, that they don't degrade or clump together over time?
Right, that's another big one, especially when you want to use these nanocatalysts out in the real world, right? They need to be able to handle some pretty harsh conditions. The lecture mentions a couple of different strategies, things like using these protective coatings to kind of shield the nanoparticles or embedding them in porous supports, to keep them dispersed and prevent them from clumping together.
So it's like creating a tiny suit of armor for each nanoparticle or building a little scaffolding system to hold them in place.
Exactly. It takes a lot of ingenuity to overcome those challenges. And it's not just technical hurdles either. There are economic considerations, too.
Right, you're talking about the cost of actually producing these nanomaterials.
Yeah, exactly. Some of the materials that are used in nanocatalysis, especially precious metals like platinum, they can be really expensive. And the lecture actually specifically mentions this in the context of catalytic converters. One of the big goals in this research is to figure out ways to use less of these really expensive materials or to find more abundant, more affordable alternatives that can still get the job done.
So it's kind of this delicate balancing act, huh? Trying to find materials and methods that are effective, durable, and economically viable.
And what about the environmental impact of all of this? I mean, are there any concerns about the potential toxicity or, any unintended consequences of releasing these nanoparticles out into the environment?
Yeah, those are definitely some very important considerations. Any new technology, especially one that operates at such a small scale, needs to be really carefully evaluated. The lecture emphasizes the need to design these nanocatalytic processes in a way that's sustainable and, minimizes any negative effects on the environment.
So responsible innovation. Makes sense. It's really exciting to think about the potential of nanocatalysis to solve some of these huge challenges that we're facing, but we also need to make sure we're doing it in a way that protects the planet, right, for future generations.
Absolutely. It's about finding that sweet spot where we can leverage the power of this technology while minimizing any kind of unintended consequences. Well, this deep dive has been absolutely fascinating. We've gone from the history of catalysis to its inner workings of these tiny particles, explored the challenges and the incredible potential of it all. I don't know, what's the one key takeaway you'd like our listeners to walk away with today?
I think the biggest takeaway is this. Even though we can't see them, with the naked eye, nanoparticles are having a massive impact on our world. From everyday products to this cutting-edge research, they're really playing a crucial role in shaping our present and our future. And the more we understand about nanocatalysis, the better equipped we'll be to actually harness its power for good.
Yeah, it's a powerful reminder that sometimes it really is the smallest things that can have the biggest impact. Thanks for joining us on this deep dive into the world of nanocatalysis. We'll see you next time.